Okay, so let's go to the next seminar by Anton Medvedev. So Anton is a research engineer at Saint-Gobain Research in Paris. He recently got graduated at Cedric CNAM, where he worked on optimization under uncertainty, and now at Saint-Gobain, he develops optimization models to support complex industrial decision-making problems. So, Anton, without further ado, we are all ears to hear your talk.
Thank you for this introduction, and thank you for organizing this seminar. So my talk will deal with some theoretical aspects of finite adaptability, which is also called K-adaptability, which was presented by Sarah. And in particular, I will talk about some asymptotic optimality result and tractability result. And this work was done during my PhD with my two supervisors, which are Safia Kedat-Sedum and Frédéric Meunier. So let's see on which problem we have the focus today. So we consider a two-stage robust optimization problem, and the complete adaptability version of this problem is written here. So we have some x variables which have to be common to all the realization of uncertainty omega, and y variable, which is wait and see variable, recurse variable also called, which can depend on omega. And we have the constraints here. We can see that the matrices A and B and the right-hand term vector B depend on omega, and omega belongs to the uncertainty set big omega. And we want to find the optimal x and y functions. So this problem, which I presented before, is very complex, and there are several adaptations or simplifications of this problem. And one of which of these simplifications is finite adaptability, which was introduced by Bertsimas and Karamanis in 2010, and it consists to restrict the possibility of the y recurrence function to constant piecewise function. So here we want to cover the uncertainty set with k parts, big omega 1, big omega k, and for each of these parts assign a fixed recurse yi. And so the problem we consider, adapt k of omega, is written as here. The difference with the problem, the complete adaptability problem, which we saw previously, is that y cannot depend on omega as before, but it's fixed for the considered region omega I. So first I will speak about the asymptotic optimality of this approach. So having these two problems, adapt k and comp adapt, a natural question is how adapt k behaves when k tends to optimality. So under which condition we have the convergence of the value of adapt k to the value of comp adapt when k tends to plus infinity. In the original paper by Bertsimas and Karamanis, they provide the following continuity assumption, and they claim that under this assumption we have the desired convergence. So let's see what is this condition. So for any positive epsilon, and for any realization of uncertainty omega in the set of omega, there exists a radius, positive radius delta, and a point x, y, which is feasible for considered omega, and within of epsilon of optimality, meaning the value of this point x, y is at most distant from the optimal value of the complete adaptive problem by epsilon. And moreover, this point is feasible on a ball centered in omega of radius delta. And here we claim that this condition is not sufficient. And I want for you to pay the attention here on the place on which x is chosen. X here is chosen after we choose the value of uncertainty omega, which may seem strange as in the original problem comp-adapt, we must choose x to be the same for all uncertainty realizations. And that's how we constructed the counterexample. So let's consider the following problem and see that we do not have the desired convergence. So the problem is the following. We have the objective to minimize x1. And the first constraint is that y omega has to differ from omega by at most x1. And then we have also this second constraint that x2 is lower and upper bounded by these terms that you can see. And x1, x2, and y belong to 0, 1. And the uncertainty set here is the segment 0, 1 as well. So first point, I want you to trust me that this problem verifies indeed the continuity assumption by Bertmas and Kermanis. And for details, you could consult our preprint on arXiv. Let's now see what is the complete adaptability solution of this problem. So if we take x1, x2, and equal to 0, and the y omega, the identity function, which as I said, omega to omega, the value of this problem will be 0. So let's see if it works. So if x1 is equal to 0, then the first constraint forces y omega to be equal to omega, and the second constraint forces x2 to be 0. So the proposed solution works in the framework of complete adaptability. And then we say that the k-adaptability version of the problem has no solution. And let's see why. If x1 is 0, then the first constraint will be that y omega has to be equal to omega. And in the framework of k-adaptability, it is not possible because y can take only finite number of values. Then let's suppose that x1 is strictly positive. Then the second constraint has to be feasible for all realization of omega, in particular for omega equal to 0. So x2 has to be lower than x1 times 0, 1. And at the same time, this constraint has to be verified for omega equal to 1. So x2 has to be greater than 0, 9 times x1. And these two constraints are infeasible. x2 has to be greater than 0, 9 times x1 and lower than 0, 1 times x1, where x1 is strictly positive. That's why we have no solution for the k-adaptability version of the problem. In this example, we have an infinite gap between the versions, complete adaptability version and k-adaptability version of the problem. But we also were able to construct in a counterexample with a finite gap. And we propose as well a modified continuity assumption. And we just move the choice of x before the choice of y, of omega here. And then we were able to prove that this modified continuity assumption provides the desired convergence. So let's see what this condition is. It is exactly the same as the one proposed by Bertmas and Kermanis. So, but here we fix x before fixing omega belonging to the uncertainty set. So next I will talk about the tractability of the k-adaptability problem. So here we will focus on the version of a problem where the uncertainty lies only in the right-hand term, only the vector b depends on omega, and from now on, matrices A and B are deterministic. So this problem is called pk of omega, and Bertsmas and Karmanis proved that pk of omega has NP hard even when k is equal to 2 and omega is a simplex. And we have the following theorem that for k equal to 2 or 3, the problem is a polynomial when the number of vertices of omega is fixed. So let's now see a sketch of proof of this theorem. And we will focus on the case k equal to 3. So the problem we consider is the following. We want to minimize this objective. And the constraints here are that we want to each omega I to be feasible on the set big omega I, and sets omega 1, omega 2, omega 3 must cover the uncertainty set omega. Let's denote by big T of omega the set of two faces of omega. And the first lemma we proved is that there always exists an optimal solution of a problem P3 omega, with omega 1, omega 2, omega 3 being polytopes, such that these vertices of these polytopes belong to the set of vertices of the uncertainty set, to the edges of the uncertainty set, or to the set of two faces of the uncertainty set. And also, these polytopes have to satisfy some extra conditions, which are technical, and I will, in the presentation later, make a focus on one on the extra conditions. But this is a quite strong result, because when we have this problem P3 omega, we do not have any idea which is the form of these omega i's. And here we can say that an optimal solution of the problem, there always exists an optimal solution, sorry, with omega 1, omega 2, omega 3 being polytopes verifying some conditions. And we also have the other side which helps us in prove that our algorithm works, which I present later, is that all polytopes omega 1, omega 2, omega 3 verifying the following conditions. So the first condition is that the vertices of the omega i's have to belong to the set of vertices of omega, two edges of omega, and two faces of omega, and verifying some extra conditions form a feasible solution of P3 omega. So this is quite a converse statement of the first lemma. So having these two lemmas, which I didn't prove, I know, but let's use them directly. I imagine they are true. We can enumerate the configurations of polytopes omega 1, omega 2, omega 3, satisfying lemma 2. And there are overall 7 to the power of some number of vertices of omega and edges of omega. And when number of vertices of omega is constant, this quite big quantity is constant as well. And for each configuration, we solve a linear program. And lemma 1, which says that there always exists an optimal solution with some polytopes respecting some conditions, ensures that if we proceed this way, we do not miss the optimal configuration of omega 1, omega 2, omega 3. So let's focus on one of the extra conditions here. As I said, we'll come back to this first lemma, and the condition we focus on is the following. If we consider a two-phase big omega prime of omega, if omega 1, omega 2, omega 3 do not pairwise intersect on the boundary of this two phase, then the vertices of omega I intersected with this phase, omega prime, are on the boundary of this phase. So we are able to eliminate some vertices if there exist, and to say that the vertices will belong only on to the boundary of the faces on which omega 1, omega 2, omega 3 do not pairwise intersect. So a sketch of this proof will be the following. So the condition we focus on is here, and just to recall, it's the same as on the previous slide. And we denote by Fi the intersection of omega I and the boundary of the face omega prime. The lemma that we have is that if we have three closed sets F1, F2, F3 covering the boundary of omega prime, if they don't pairwise intersect, then the convex holes of these sets cover omega prime. And having this lemma, we are able to update omega i's on the two-face omega prime by taking the convex hole of Fi defined previously. And so let's see a proof of this lemma. So we have the following image here. Imagine we have this pentagon, which is a two-face omega prime, and it is covered by the boundary is covered by three convex closed sets F1, F2, F3. And so F1 is red, F2 is blue, and F3 is green. Let's, without loss in generality, suppose that F1 intersected with F3 is empty. Here it is the case, so the red and the green do not intersect. Let's take any point belonging to the interior of omega prime of this pentagon, and let's draw a small circle around it and construct B1, B2, B3 as follows. So we take from X a ray hitting the boundary of omega prime, and we color the point it crosses on this circle as the same color as it hits on the boundary. So by this construction, we have that B1 intersected with B3 is empty. And by corollary of a Fan's theorem, we have that one of the BI contains antipodal point, which implies that one of Fi contains an antipodal point, which implies that that X belongs to the convex hole of this Fi. And then we finish the proof of this lemma. So to conclude, we saw a condition under which we have a desired convergence of finite adaptability to complete adaptability, and then we have some results on the polynomiality for k equal to 2 or 3 of the version of a problem where matrices A and B are deterministic and the uncertainty lies only in the right-hand term of the constraint. And the open questions we can have is that it is very nice to have this condition, but when we deal with real problem, is there a simple way to verify this modified continuity assumption in practice? And we weren't able to answer this question yet. And then next question is dealing with tractability. We have there is a complexity result for k equal to 2 or 3. And can we generalize this result to any k? So having a fixed number of vertices of omega, is there some complexity result or bound? So it remains an open question. Well, thank you very much for your attention.